Hi, and welcome back to our class on the practice and pitfalls of studying organic reaction mechanisms. We've made it now to lecture 3, and I have the pleasure of recording this short introduction in a rare state of affairs where I'm sitting in a sunny office in Glasgow. Now it sounds cheesy to mention that, but it has some relevance to this lecture in which we focus on temperature effects in studying reaction mechanisms. At the heart of this slightly shorter lecture, we're really comparing two very key and important tools in using temperature to study mechanism. Those are the Arrhenius relationship and the Eyring equation. So we compare and contrast both of these tools, which are subtly but crucially different and can cause a lot of confusion in terms of how they are applied to study reaction mechanisms. I'd also like to thank my friend and former postdoctoral colleague, Dr. Alex Cresswell, who at the time of this recording is at the University of Bath, for giving me some inspiration and help with the slides that you're about to see. So it's a great pleasure for me to call this lecture a little bit more of teamwork rather than an individual exercise solely from me. So without further ado, I really hope you enjoy lecture 3 on using temperature to study reaction mechanisms. Hi, and welcome back to the course on the practice and pitfalls of studying organic reaction mechanisms. We're now on lecture 3, and this time we're talking about how temperature can be used as a tool to study reaction mechanisms. You may remember this scheme from lecture 1, in which we looked at a hypothetical Arbuzov reaction between an alpha bromo ester and triphenyl phosphite to form a phosphonate ester and ethyl bromide. First time round, we were interested in breaking up this two-step reaction into its elementary steps and understanding how we would define the rate laws assuming all species shown were involved. This time, we are concerned with what was simply extra information in lecture 1, the information concerning the temperature effects, the information concerning the Arrhenius rate law, and the Eyring equation. One is empirical, the other analytical. One concerns the overall or macroscopic observation, and one is used to tease out insights from an elementary step. In this lecture, we're exploring the uses of these tools and the confusion in using these tools in more detail. We'll go through them one by one and then draw some essential comparisons between them. Starting with the Arrhenius rate law, this was first developed in 1889 when Svante Arrhenius proposed the equation in the grey box, where K is the observed rate constant, A is the pre-exponential factor, which has a weak temperature dependence, but for the sake of simplified analysis is assumed to be a constant. E subscript A is the empirical activation energy of the reaction, R is the gas constant, and T is the absolute temperature. Taking the natural log of both sides of the Arrhenius equation derives a linear form as shown in the graph, where reciprocal temperature 1 over T can be plotted against the natural log of the rate constant ln K, giving an approximately linear relationship within a small temperature range. The slope or gradient of the line equals the negative activation energy divided by the gas constant. Some simple rearrangement gives the activation energy. The y-axis intercept gives the natural log of the pre-exponential factor A. When we unpack the Arrhenius equation, it's important to note the position of temperature and consider the effect this has on the rate when temperature is altered. Because temperature is part of a denominator, higher temperatures lead to lower activation energies. And because activation energy appears in a negative exponent, it means that lower activation energies lead to higher rates. It makes intuitive sense, but it's always worthwhile working through the equation to see what happens when the variables in the equation are changed. The form of the Arrhenius equation can be likened to that of the Boltzmann distribution, which describes the population of energy states at a given temperature. In this light, we can say that the rate constant is proportional to the fraction of molecules with an energy greater than some threshold, the activation energy. Look at the diagram on the right. Here, you can see the distribution of particle energy for two different temperatures. As we go from low to high temperature, the particle energies spread out, and more are at an energy above the threshold. The Arrhenius relationship, strictly speaking, is only applicable to ideal gases, as is the Boltzmann distribution, but it is often used with useful results in condensed phase applications too. Having considered the Arrhenius relationship in more detail, let's now look to the Eyring equation. This was developed later than the Arrhenius relationship. The most crucial difference is that Eyring's equation was derived from transition state theory, yielding the equation in the grey box. All the variables are defined here on the slide, but a few elements are worth highlighting. Oftentimes, the term involving M, reaction order, is missed out from the Eyring equation, but it is an important consideration if the equation is used and understood properly. Note too, in the temperature term, it looks a lot like the Arrhenius equation, but now we state delta G trans rather than E subscript A, because the Eyring equation is derived from transition state theory, which relates to a single step, the rate limiting step, of a reaction. Again, we can form a linear version of the equation, given the graph on the right hand side. This time, the slope allows calculation of the enthalpy of activation. The y-intercept allows us to find the entropy of activation. For the simplest case, a first order unimolecular reaction, the Eyring equation is expressed as shown in the bottom grey box on this slide. The term involving the reaction order and the transmission coefficients has been removed as it collapses to a value of 1. The linear form of the Eyring equation can be more easily understood when the original equation is expanded into terms of enthalpy and entropy rather than the combined expression of free energy. Recall that delta G equals delta H minus T delta S. The expanded Eyring equation is therefore what we see in the top grey box on this slide. When we derive the linear form of this expanded equation, we reveal the relationship shown in the bottom grey box, the red terms showing the y and x axis of the linear plot respectively. If we now start to compare both equations, Eyring versus Arrhenius, we can see the gross similarities in their form and how a linear relationship is plotted in both cases. Note that similar does not mean the same. We'll come back to this comparison and clarify the major differences between these mechanistic tools in a later slide. The final thing to note here is the reference provided at the bottom of the slide. Particularly in the case of the Eyring equation, it is often assumed that enthalpy can be calculated more accurately than entropy of activation. This assumption comes from the sensitivity of the y-axis intercept to small changes in the plotted data. This assumption is false. There are alternative linear forms of the Eyring relationship in which the entropy of activation is derived from the linear slope and the enthalpy is taken from the y-intercept, so the opposite to the case that we have on the slide. You can read the paper to find out more. Let's stay with the Eyring analysis for now and unpack the terms in some more depth. We've already mentioned the key components extracted from this analysis, those being the enthalpy of activation and the entropy of activation. Whilst enthalpy is almost always positive, entropy of activation can be negative, near zero, or positive, making it a more discerning mechanistic tool. It is interpreted as a measure of order or available degrees of freedom on approaching the transition state. In the middle of the slide, we can see some exemplar systems and their associated entropies of activation. Along the top row, we see 3 different second-order processes which require significant order in the transition state. They all carry negative entropies of activation. Conversely, the fragmentation reactions on the bottom of the slide represent increasing degrees of freedom, increasing disorder on approaching the transition state. These reactions each carry positive entropies of activation. Note that for catalytic reactions, the observed rate constant K obs should be divided by catalyst concentration to get the true rate constant, and this is almost always forgotten. Finding the true rate constant, first, second, or other, for the rate or turnover limiting step is crucial in being able to use and interpret the Eyring equation properly. Use of the wrong rate constant can lead to wrong mechanistic interpretation of your data. We can take the comparison further by asking the question, which equation describes multi-step reactions? On the left, the Arrhenius equation involves an observed rate constant K obs and is derived empirically from experiment. On the other hand, the Eyring equation is analytically derived from transition state theory and first principles. The equation centres on a single elementary step. The Arrhenius equation is thus the most appropriate for looking at the combined or macroscopic effects of temperature on observed rate of a multi-step reaction. Another way to think about this is that there is an Eyring equation and delta G trans for each and every step in a multi-step reaction. If there are any steps before the rate limiting step, then the Eyring parameters calculated will be a composite of all steps up to and including the rate limiting step. In short, the parameters calculated from an Eyring analysis can be very difficult to interpret correctly. You might then ask, are Arrhenius and Eyring equations equivalent for a single step reaction? Ultimately, no. They are each derived from 2 different formalisms, Arrhenius from collision theory and Eyring from transition state theory. One way to show this difference is in the last exponential term of each equation. On the left, the Eyring equation involves an enthalpy term, which is weakly temperature dependent. Conversely, the activation energy term in the Arrhenius equation on the right is temperature independent. The precise relationship between these equations is dependent again on the molecularity of a reaction. In other words, the relationship between delta H trans and E subscript A, and between delta S trans and A, is different for uni and bimolecular processes. See the 4 equations in the grey boxes near the centre and bottom of the slide. And because RT is small at room temperature, only 2.5 kilojoules per mole, compared to the typical range of delta H trans values 20 to 150 kilojoules per mole, you will often see activation energy and delta H trans quoted as approximately equal at room temperature. For all our comparisons between Arrhenius and Eyring plots, we have assumed that the linear forms of both equations are always linear. However, there are various cases in which the plots deviate from linearity. In our first example, quantum tunnelling can cause concave curvature on an Arrhenius plot. This is demonstrated for the tautomerization process depicted at the top right of the slide. Another example of curvature occurs when there is reweighting of the enthalpy and entropy dominance in a multi-step sequence, such as that shown on the bottom left of this slide. It might be the case that below a certain temperature, step 1 is rate limiting, and that both steps have differing enthalpy and entropy features. A hypothetical resulting break in the linear Eyring plot is shown in the bottom right of this slide. A further example of linearity breaks in Eyring plots comes from enzyme reactions. We might, for example, have the case where the active site of an enzyme significantly changes shape above or below a certain temperature, changing the overall mechanism of the reaction under study. From the diagram on the left side, the effect is manifest in turning on an additional pre-equilibrium step at the enzyme active site below 30 degrees. A literature example of this phenomenon is shown on the right side, where two clear regions of linearity on the Eyring plot are shown in the data. In addition to looking at the nature of enthalpy and entropy of activation in an elementary step, temperature studies and the Eyring equation can be employed to study various modes of selectivity. Kinetic selectivity is concerned with rates rather than product stabilities. We can therefore define a product ratio P as the ratio of rate constants for two competing processes. The linear form of this equation allows us to plot a linear trend from 1 over T versus ln P. We can draw out a simpler example of using temperature to study kinetic selectivities by using the Arrhenius relationship. On the top left of this slide, a cyclopropane is observed to decay to the carbene shown in the box. This carbene then degrades further via two competing processes. K subscript T is via hydride transfer, and K subscript A is via addition across an alkene. On the right, we can express the Arrhenius relationship in linear form for both decay processes. These are shown in the top two equations on the right hand side. The ratio of these equations is shown in the third grey box, wherein we see that the plot of 1 over T versus the natural log of Ka divided by Kt gives a linear trend. The resulting plot from the example gives a gradient from which the difference in activation energy for each decay pathway can be calculated. In this case, the addition process, K subscript A, has an activation energy 1.6 kcals per mole, higher than that for the hydride transfer, K subscript T. So overall, that brings us to the end of Lecture 3 on the uses of temperature effects in deciphering reaction mechanisms. We've looked at how reactions at higher temperature can be thought of as having a higher number of particles above a threshold activation energy. We've also compared two similar but subtly and crucially different models from which to study the effects of temperature on rate constants. The Eyring relationship derives from transition state theory and deals with a single elementary step. The Arrhenius relationship instead dealt with observed rate constants for multi-step processes and is derived empirically. We then went on to see that the plots used as tools in both Eyring and Arrhenius analyses can present cases of non-linearity. And finally, we started to appreciate that we can use the temperature effects to study competing processes, to study selectivity, as well as study the details of an individual reaction. So thank you for watching this lecture. I really hope you've found it useful and will be able to use this when you bring temperature studies into your own mechanistic analyses. We'll see you back here for Lecture 4 soon. Thank you very much.